Hello everyone, before I start the video, it's not a professional if I don't introduce myself. Hi guys, my name is THUFEIL, I'm from Intech 17 and I'm here to guide you through a critical area of study, and for the material right, I will give some information about the biomechanics in upper limb orthosis and upper limb prosthesis, design of the upper limb orthosis and upper limb prosthesis, and the last one is the components of upper limb prosthesis. This lecture is designed to provide you with a solid foundation in the principles that govern the design and function of the upper limb prosthesis. By understanding these concepts, you will be better to innovate, improvement, and ultimately enhance the lives of those who rely on this device. So, let's begin. For the first lesson is about the biomechanics in upper limb orthosis and upper limb prosthesis. For the first one, we will talk about the lever concept. Do you guys know or ever heard about the lever concept in biomechanics? So, a lever in biomechanics is a rigid object used with an axis to multiply the mechanical force or resistant force to operate it. The lever efficiency is measured by a mechanical advantage, which is the ratio between the effort arm and the resistance. So, the formula for searching the lever efficiency is efficient lever requires a less effort. There are three classes of levers based on the relative positions of the fulcrum load and effort. The first class, second class, and the third class of lever. I will give some examples in here. For the first one, you can imagine lifting a rock with a lever. If the distance from the fulcrum to where you push is twice the distance from the fulcrum to the rock, you only need half the force to lift the rock. Okay, I will just give another example. And this example is talking about the biology question. Just imagine there is a hand was holding a book. The position of the elbow is flexed. So in here we can see the axis here is the elbow because it can bend up and down the forearm. The next one is the book. The book is the resistance because the book has a weight. That weight is due to gravity pulling it down. And the last one is the bicep. Became the force because the force came from the biceps actively pulling to lift the book. Without the bicep contracting and pulling, there would be no movement and the book would just stay put due to the gravity, or it can be fall down. We will talk about the processes biomechanics. Can you guys imagine why is the biomechanics important to the prosthetics? So the biomechanics help us design prosthetic limbs that are comfortable, efficient, and functional. It ensures the prosthetic interacts well with the body. In here, we have two types of stump. There are the short stump and the long stump. Do you know what is the difference of these two types of the stump? So a longer stump generally provides more surface area for the force distribution, making the prosthetic feel more stable. And for the shorter stump can concentrate force, potentially causing discomfort. So the shorter stump need careful socket design and cushioning, while longer stumps benefit from stability with ongoing monitoring and education crucial for the both. So we have explored the world of upper limb prosthetic of the biomechanics. from the basic concepts of the levers to the analysis of the force on prosthetic sockets. I hope you gained some new insights. Now, let's leave the biomechanics world for a moment and move to a new adventure in a design of upper limb orthosis and upper limb prosthesis. Let's go. Welcome to the second session, and in here we will discuss about the design in upper limb prosthesis and upper limb orthosis, because in orthosis and prosthesis there are a lot of design. So let's start from the upper limb prosthesis design. The first one is the transradial socket design. The sockets should be designed to accommodate the stump, provide a good force transmission, and use as much residual limb movement as possible. For the basic design of upper limb prosthesis, the first one, there is a design of plug fit, or the standard one. The second one, there is a northwestern supracondylar socket. The third one is the Muenster. The last one is the Strathclyde supraolecranon socket. And now we will talk about the upper limb orthosis design. In upper limb orthosis, there are some type of design. The first one, there's a static polar wrist hand orthosis with a thumb hole. And the second one, there is a resting wrist hand orthosis. For the simple polar orthosis, the function is to stabilize the wrist, to immobilize the wrist joint, and to prevent the contracture. And for the resting wrist hand orthosis, the functional is to stabilize the wrist, MCP, DIP, and PIP joints of the thumb and the fingers, and to reduce pain and inflammation. After we know about the design in upper limb orthosis and upper limb prosthesis, I will explain about the complementary of upper limb prosthesis. And now let's change to the next session. Let's go! Hi guys! Right now we were at the last topic about the components in upper limb prosthetic. This presentation will cover the key components used in upper limb prosthetics, their functions, and the materials they are made of. So let's start with a quick overview of the main components that we will be discussed right now. So there is socket and the materials, there is hand grips, and there is a terminal device, and cosmetic covers, or we can say they're glove cosmetic, and there is a wrist units, elbow units, shoulder units, and there is a cable control system, and the last one is the harnessing. So for the first one, we will talk about the socket. The socket is a crucial component for accommodate of the stump, providing suspension and transferring force and motion. Common materials include lamination by acrylic or polyester resin, polypropylene or leather, and interface or liner options like a silicone or pellet. For the second one, there is a hand grips. The hand grips are essential for enabling pinching, grasping, and manipulation. The main types include, for the first one is thumb finger pinch, the second one is digitopalmar grip, and there is a hook prehension. And there is a terminal device. The terminal device can be either passive or not requiring voluntary muscles, or we can say a cosmetic hook. And the second one is the active one that should be requiring voluntary muscles. It can be voluntary opening or closing hook. And there is a cosmetic gloves. These are designed only for cosmetic purpose and can be made of silicone. It's easier to clean, more cosmetic, but more expensive and easily get damaged. And we can use a PVC, more elastic, cheaper, resistant to weather and chemicals, but easily absorbs stains. Next one, we will talk about the wrist units. The wrist units serve to attach the terminal device to the prosthesis and allow to active or passive pronation and supination. The types include quick disconnect, wrist flexion, friction type, and ball and socket wrist joints. Next one, we will talk about the elbow units. The elbow units come in various types. For the first type is a block type. It's a functional elbow unit, manual locking elbow unit, and a single axis elbow unit. And the second type is a flexible hinge and a rigid hinge. After that, we will talk about the shoulder units. The shoulder units are not always necessary for shoulder disarticulation or fourth quarter amputation. The function of shoulder units is to allow passive movement for positioning the prosthesis. Next, we will talk about the cable control system. These systems include, for the first one is a single bolted system, and there is a dual or fair lead system. And the last one is the harness. The harness provides suspension through the socket, transfer of body power to control the cable, and these harnesses had some common design such as a figure 8, figure 9, or a shoulder saddle harnesses. Next one, we will talk about a control of prosthetic components. The components can be controlled by a body powered systems using a harnesses, control straps, cables, and a body movements. And there is a externally powered system using an external power such as a batteries, and we can call it a myoelectric system. Now we will talk about the myoelectric system. The myoelectric control, it involves a prosthesis controlled through the muscle impulses. Then the electrode is placed on the skin to receive the electrical impulses. Bionic hands. The bionic hands are designed to mimic the natural movement of the human limbs, often utilize osteointegration, connecting the prosthesis directly to the bone.